Thanks Dan and Brett for organising this. I think it's a great initiative, and I just before I start, like to thank particularly Joe. It's been a really great collaboration, this bit of work, and it's really exciting that we're starting to see some results from this, and I really hope that we can continue working together in the future. So thanks, Joe. As Tim was getting to, this project is really trying to ask this question about if we were to implement stormwater source control measures or low impact development all through a catchment, what would be the impact on flooding? If you go to the next slide, Tim did a very good job of explaining this already and stealing my thunder, but the point here was just to really emphasise that urban flooding is a consequence of not only impervious surfaces but also the stormwater drainage system. So more impervious surfaces connected to stormwater drainage systems, urban flood risk is higher. If you go to the next slide, again, this is a point that Brett did a good job of explaining that in many areas, stormwater-related flooding, so this nuisance flooding is a serious problem. This is just a picture of Elizabeth Street in Melbourne under a big flood. So again, this sort of nuisance flooding, this stormwater-related flooding, is a real problem for many areas. Go to slide 4. Anita and Brett also spoke about the traditional use of hard engineering solutions to alleviate or mitigate urban flooding, so the sealing of urban channels, construction of levees, things like that. But we know those sort of solutions. Go to the next slide.
I think we lost you for a second there, Matt. Are you able to swing back for a moment and go through that slide one more time?
The slide is an alternative approach to flood management, that one?
It was the fourth slide.
So the fourth slide, I was making the point that traditionally managers have used hard engineering solutions to alleviate or mitigate urban flooding, so sealing of urban channels, construction of levees, things like that. But these approaches don't address the stresses to urban streams. And so if you go to the next slide, slide 5, a possible alternative approach to flood management in urban areas is retrofitting the drainage system with stormwater source control measures or water sensitive urban design, low impact development, all these great terms. And the benefit of using low impact development is that not only potentially can it have impacts on urban flooding, but as Tim was getting to, it can. We're seeing early signs that it could restore the health of urban streams. There are other benefits of low impact development systems. So rain gardens, for example, put more water back into the ground. There's benefits in terms of microclimate. Other source SEMs like rainwater tanks can augment the water supply network, reduce our demand for potable water. So there's all these great benefits of using stormwater source control measures, and not a lot of researchers have really understood what the catchment scale implications in terms of flooding are of these systems, and that was really our aim here. So we go to the next slide. Again, really this potential of using low impact development for flood management at large scales is really untested. There's a lot of researchers have done work, our group, for example, looking at the performance of stormwater source control measures at very small scales, so at household scales or at the streetscape scale. And those studies have shown that these systems are very effective at reducing stormwater volumes and peak flows, but very few researchers have used real catchments to. Okay. So I'm on slide 7 here. So again, our aim here was to demonstrate the catchment scale flood benefits of retrofitting Little Streamback Creek with stormwater source control measures. And we did this by coupling of two models. So we used an urban. The University of Melbourne side was doing the hydrologic modelling and then passing lots and lots of data to Joe to do the hydraulic modelling. And go to the next slide, slide 8. As I was saying before, our task here was to model the hydrology of Little Streamback Creek primarily under two different scenarios. So one scenario being Little Streamback Creek under catchment under current conditions, and then to model a catchment under a case where every single household had a rainwater tank or rain garden. All the road surfaces in the catchment were treated with some kind of low impact design measure. And then I might talk a bit slowly then if I'm lagging out a bit. And so after running the hydrologic model, we produce all these flood hydrographs, which we then send to Joe to do the hydraulic modelling. And so the focus of my talk is going to be on the hydrology, and then Joe's going to talk about the hydraulics. We go to slide 9. We built two different hydrologic models or music models of the LSC of Little Streamback Creek catchment. And I should also say that music is just one of the models out there that can model these SEMs. So you guys in the States have experience using the SWIM model. And we could have equally done this work using SWIM. We've done very similar work using SWIM, but we chose music in this case. But we could have also used SWIM. So we built a model of the catchment based on the current conditions, and so this model we took into account the existing stormwater source control measures that have been built that Tim spoke about before, roughly the 300 systems that have been built. And this model was calibrated to the observed data we've been collecting. I should say Little Streamback Creek isn't a catchment where flooding is a serious problem. But the primary reason we chose Little Streamback Creek was because of all this great data we had and hydrology data that we could calibrate models with, really great LiDAR data that Joe could build his hydraulic models with. So, so flooding isn't really a problem in the catchment, but because we've got all this great data, we can use that to test this question. And then we also built another music model.
Yeah,
I can try to tell you
your video.
Okay, is that working a bit better?
Yeah, I think that's better.
Okay, now you don't have to look at my face, which might be an improvement as well. So, as I was saying before, so we built two music models of the catchment. So, a model based on the current conditions, so taking into account the current level of SEMs. This model was calibrated to the real data. And then we also importantly built a model of the catchment, a hypothetical sort of scenario where we said, what if we put SEMs treating every impervious surface in the catchment? So, and we're talking about SEMs, we're talking about rainwater tanks used at households and rainwater tanks used for things like toilet flushing, clothes washing, hot water usage. So really trying to get as much internal demand as possible. Also using rainwater tanks for garden watering as well. And in addition to treating the roof areas with rainwater tanks, also using rain gardens to treat particularly non-roof areas. That are rain gardens that are sort of 1 metre deep, 300 mil of extended detention, these sort of vegetated infiltration systems. So we built So go to the next slide, slide 10. Having built these music models, and part of building these music models is we took a lumped approach to modelling these different stormwater source control measures. So we could have, Tim could have spent the last 6 months of his life modelling hundreds of individual rainwater tanks in this model, and it would have taken a very long time to run. Instead, we took a lumped approach whereby instead of modelling 100 5,000 litre tanks, we modelled one 500,000 litre tank. So it's sort of a semi-distributed hydrologic model, if you like. And further improvements on this modelling could be that a much more distributed modelling setup, but the case here was to take a more of a lumped approach to modelling the different SEMs. Of course, if you're modelling at smaller scales, it would be more feasible to be modelling individual systems, but because we're looking at this larger catchment scale, we took this sort of lumped approach. Move to slide 11. I thought I'd just quickly talk about the sort of input data, climate input data into this model. So we used some design rainfall events, something Amir and Brett were talking about before, these intensity, frequency, duration curves. So we extracted from our local Bureau of Meteorology 84 different design rainfall events, so events that range from sort of 10 minutes to 24 hours, and we consider a whole range of average annual return intervals, so very frequent events, sort of 1 year events, and also very rare events, so 1 in 100 year events. And then after getting these events, we disaggregated them using sort of storm temporal patterns that are sort of industry standard. All these 84 events for each scenario, so the scenarios being the catchment under current conditions and the catchment with complete application of SEMs. All these rainfall events were modelled in one simulation, so that allowed us to run all 84 design rainfall events at once. We go to the next slide, slide 12. Having constructed all the models and gathered all the input data, both these music models were executed, and we extracted flood hydrographs for each scenario, and importantly also extracted the flood hydrographs at multiple points in the catchment. So that's important because these hydrographs at different points in the catchment became inputs into Joe's hydraulic model, which we'll speak about next. We go to the next slide, slide 13. Of course, doing this resulted in lots of hydrologic data, but just quickly, so for each scenario, there's catchment under current conditions and catchment with complete application of SEMs. The output included 7 hydrographs for each of the 84 rainfall events, and today I'm going to be just comparing some peak flow differences between sort of catchment under current conditions and catchment with SEMs at the catchment outlet, and then of course all these hydrographs became input into Breezo to run the hydraulic model. So go to the next slide. The slide after this is probably a very hard to read graph, so I thought I'd explain a little bit before I get to it. But the next graph is just going to what we're going to do is compare the maximum predicted peak flow for the Little Sheenbark Creek catchment under current conditions versus a catchment with complete application of flow impact design, just for the catchment outlet. And here are some results. So slide 15. So the x-axis is the different durations for these storm events. The y-axis is the peak flow in cubic meters per second. And these different panels, 1, 1.44, etc., up to 100 represent the return period. So 1 in 1 year event to the 1 in 100 year event. And the red line is all the predicted results from the catchment under the scenario that we've got complete application of stormwater source control measures. And the green line is the catchment under current conditions. And you can see here that all the SEMs are doing what I think is a pretty good job, even up to the 100-year event for the shorter duration storm events, even up to, say, the 60-minute storm event. But once you start getting into these longer duration storm events, the effect of the SEMs is really not much at all. And thinking about this, it makes sense because a lot of these stormwater source control measures are designed to retain, say, 10, 15, 20 millimetres of rainfall. And that sort of magnitude of rainfall matches quite nicely to a lot of short duration design rainfall events. But when you start looking at 3-hour, 6-hour, 12-hour storm events, we're talking sort of 100 millimetres of rainfall, and so you can see why these SEMs aren't so effective for these very long duration storm events. But I think it's pretty encouraging, and Joe's going to show some pretty neat results soon, that in terms of the hydrology at least, that a catchment scale application of SEMs can have some pretty significant impact on reducing flood peaks, particularly for short duration storm events up to even the 100-year ARI. So just on my last slide, just to conclude before going to Joe, our work is suggesting that that a catchment scale implementation of LID can have a significant impact on reducing the magnitude of short duration storm events, but little impact on longer events. Yeah, so thanks for that, and Joe's going to now talk about is the hydrologic modelling and showing essentially what these reductions in hydrology mean in terms of flood extents and things like that. So thanks a lot.
Great, thanks. Did anyone have any questions for Matt before
I was wondering, so the SCM that you implemented in this simulation, could you imagine increasing the retention of the longer duration storm events through some change in the LID or the SCM infrastructure itself, or do you feel like there's an absolute hard upper limit on the amount of rainfall that can be retained in these systems?
Yeah, good question, Stan. Yeah, these systems have pretty much been designed in a way that they're working pretty much as hard as they practically could. Unless we want to start expecting everyone to start drinking tank water and things like that to really improve their performance. Yeah, it would be difficult to expect them to perform much better than they are here. But I think the thing with this flooding is that we know flooding is a very catchment-specific phenomenon, and so if your catchment is one where the critical storm duration, the storm duration that is primarily responsible for serious flooding, and if it is a critical storm duration of a magnitude of maybe 30 minutes to 1 hour, that these SMs could have a really significant impact. Of course, if you're looking at very large catchments, then where the critical duration for those larger catchments, it could be 12 hours or 24 hours, their effect could be not so much. So.
This is Brett. If I could jump in, are you hearing me?
Yeah.
Okay. I do like the way you looked at the duration of the rainfall and the return period as kind of two, independent variables. It does sort of help us to frame, what parts of the system we can maybe see some changes to the, on I guess the demands we're placing on the drainage infrastructure, right? So perhaps way bottom of the pipeline is a more challenging place to rethink, or how much we can expect to reduce in terms of the needed capacity of the drainage network. But as we work up our way into up the watershed, it does sort of, I think, show that there's sort of maybe more nuanced answers to like whether or not we can really redesign the drainage infrastructure based on a reduction of the storm flows, 100-year type storm flows. So anyways, I like the way you've kind of looked at both the return period and the rainfall duration separately.
Yeah, thank you, Brad. That's one possibility with all of this is that, for example, in an existing urban area, in an area where, say, flooding is a problem, often one solution is to upgrade the downstream pipe to be much bigger. I suppose there's great potential with SEMs that if we implement them in this catchment, maybe we don't need to sort of upgrade the pipes downstream and things like that. So, yeah.
Okay. Well, thank you very much, Matt. I think also in the interest of time, I suggest we keep rolling along here and turn the microphone over to Jochen, who's going to present the hydraulic modeling that followed up on this hydrologic modeling.